You know, it's pretty wild when you think about it. Every single movement in the universe, from you just walking down the street to a planet orbiting a star, it all follows the exact same, surprisingly simple set of rules. Today, we're going to pull back the curtain on the physics that makes everything go. So, let's jump right in by looking at the simplest motion there is.
It all kicks off with a really basic question. When you push something, a box, a car, anything, what's actually going on there? I know, it seems super obvious, right? But the answer? Well, the answer is kind of the blueprint for how the entire world works.
See, here's the thing. When you push something forward, the universe actually pushes back. It's a constant battle. The push from a car's engine is always fighting against these other forces, like friction from the road or air just getting in the way. So motion isn't just about moving forward, it's about winning this constant tug of war against all the things trying to slow you down.
Now, what's absolutely incredible is that this whole complex battle can be summed up by one single beautiful rule. An equation so powerful it explains everything from how a baseball flies to how a rocket gets to space.
And here it is, the big one. F equals ma. Force equals mass times acceleration. Okay, let's break that down real quick. Force, that's just your push or pull. Mass, that's just how much stuff something is made of. And acceleration, that's any change in its motion, speeding up, slowing down, even just turning a corner. That's it. That's the secret sauce.
So what this really boils down to is pretty intuitive. Something with a small mass, say a golf ball, is super easy to get moving, right? It doesn't take much force at all. But something with a huge mass, like a freight train, yeah, that's going to take a massive amount of force to get it to change its motion. It's simple, really. More stuff means it's more stubborn.
Okay, so this rule isn't just for things we can see ourselves pushing around. It also perfectly explains all these invisible forces that are constantly acting on us and on everything around us all the time. Let's start with the big one, the one we all know.
And this brings us to something that trips a lot of people up: the difference between mass and weight. Look, your mass is just the amount of stuff you're made of, and that number is the same no matter where you go in the entire universe. Your weight, though, that's a force. Specifically, it's the force of gravity pulling down on all your stuff.
And this is the perfect way to picture it. An astronaut might have a mass of 70 kilograms. That's true on Earth, is true on the moon, and it's true floating out in deep space. That number never, ever changes. But because the moon has way less gravity, their weight, that downward pull, is only about a sixth of what it is here. Same astronaut, same stuff, just a different amount of pull.
So we know that when forces are unbalanced, things accelerate. But what about when they're not? What happens when all the forces pushing and pulling on an object completely cancel each other out? What happens when everything finds a perfect balance? Let's take a skydiver. The second they jump out of that plane, the downward pull of gravity, their weight, is way stronger than the upward push of air resistance. And because those forces are totally unbalanced, they accelerate downwards, fast.
But here's the cool part. The faster they fall, the harder the air pushes back up on them. And you can see it perfectly in this graph. Their speed shoots up at first, but then it starts to level off. That's because the air resistance is getting stronger and stronger, putting up a bigger and bigger fight against gravity.
And eventually, they reach this amazing point where the upward push from the air becomes exactly equal to the downward pull of gravity. The forces are perfectly balanced. And with no net force, there's no more acceleration. The skydiver just falls at a constant maximum speed. And that, right there, that's what we call terminal velocity.
Then, they pull the ripcord. The parachute opens, which massively increases the surface area, and that just skyrockets the upward force of air resistance. Suddenly, the upward force is way stronger than gravity, and that imbalance causes them to slow down and fast until they reach a new, much slower, and much safer terminal velocity. It's all just a game of balancing those forces. And the same idea applies to just changing direction. You know, an object in motion wants to keep going in a straight line forever. To make it turn, like this car going around a bend, you need some kind of constant force pulling it towards the center of that turn. We call that a centripetal force. And for the car, that force is just the friction between the tires and the road. If you lose that friction, well, you're not making that turn. All right, so we've seen how these rules work in everyday life, but now let's look at how understanding them in a really high-stakes situation, like a car crash, can literally be the difference between life and death. To get this, we need one more concept: momentum. It's really simple. It's just an object's mass times its velocity. You can just think of it as mass in motion. A huge truck flying down the highway has an enormous amount of momentum. A little gnat buzzing by your ear has practically none.
Okay, now here is the brutal reality of any collision. All that momentum you have, all that mass in motion, it has to go to zero. That part is absolutely non-negotiable. The only thing you can possibly change is how long it takes for that to happen.
And that brings us to maybe the single most important equation in all of safety engineering. The force you feel in a crash equals your change in momentum divided by time. Now look close. See how time is on the bottom of that fraction? That's the whole secret right there.
So what that equation is telling us is absolutely profound. In a crash, you can't change your mass and you can't change the fact that your speed is going to zero. So the only way to reduce the crushing force of that impact is to make the impact itself last longer. You have to increase the time.
And this isn't just some theory. The numbers prove it. In this crash test, without an airbag, the whole impact is over in a blistering 300ths of a second. But with the airbag, it stretches that time out to 1500ths of a second. Now, that's still incredibly fast, but by making the crash last 5 times longer, the force on the dummy is cut down by 5 times. It's a huge difference.
This is the genius behind every modern car safety feature. Crumple zones, airbags, they all do the exact same thing. They're designed to do one job: stretch out the duration of the collision. They buy you tiny fractions of a second, and in doing so, they massively reduce the forces that your body has to deal with.
You know, the thing I just love about physics is how you see a rule in one place, and then suddenly you start seeing it absolutely everywhere. The same rules that save your life in a car are the exact same ones that are choreographing this beautiful dance across the entire cosmos.
And this slide just brings it all home. Remember that inward pulling force, that centripetal force that lets a car take a corner? Well, on a cosmic scale, gravity is doing the exact same thing. It's the sun's constant inward pull that's acting like a leash, keeping all the planets from just flying off in a straight line and holding them perfectly in their orbits.
So from the simple act of pushing a shopping cart, to a skydiver hitting terminal velocity, to the way an airbag is designed, and even to the orbits of planets, it's all the same set of rules. It's all connected. So I guess my question to you is, now that you know the rules of the game, what's a motion you see every day that you'll never look at the same way again?